Hello, and in this video I want to talk about multiple stage amplifiers. That's systems built up of several amplifiers or other systems in series, and each of those blocks added in series introduces an amount of noise into the system. First thing we need to do is talk about equivalent input noise. Now, in general, an amplifier is going to have an input signal, SI, and some input noise, Ni. It will have some gain, and in the process of multiplying the signal by that gain, it will introduce some additional noise to give an output signal, SO, and an output noise, NO. Now, we can create an equivalent model of this noisy amplifier in terms of a perfect noiseless amplifier and an equivalent input noise, in such a way that the output signal is just equal to the input signal times the gain, and the output noise is equal to the input noise plus the equivalent input noise times the gain. So effectively, we're taking all of the noise sources of the amplifier and converting them to a single input noise power, a bit like we did with op-amps, taking all of the noise sources inside the op-amp and moving them to equivalent input noise sources. In this case, though, we're only going to be dealing with an equivalent input noise power. And it's worth emphasizing that this gain here is a power gain. This noise here is a noise power. This signal is a signal power. We're dealing with powers all the way. And that is so we can simply add up the noise together. You can only add up two noises, two independent noise sources, if you're adding up the powers, remember. So everything here is written in terms of power and power gain, not in terms of voltage and voltage gain. Okay, so supposing we have several of these noisy amplifiers and we arrange them in series. Something like this. What's the total noise output that we would get from this system? Well, we can start and think about what would the noise be coming out of the first amplifier stage there. And the answer is that would be G1 times the input noise, Ni, plus the equivalent input noise of the first amplifier stage, Ni1 here. That noise is going to be the input noise of the second stage. So that gets another equivalent input noise, Ni2, added to it, and then the result is multiplied by the gain of the second stage. That produces the output noise of the second stage, which is the input noise to the third stage. So that has another noise term, Ni3, added to it, and then that gets multiplied by the gain of the third stage. And we get that expression for the total noise at the output of our system. Now, we can do a bit of mathematics on that, multiply out all of these brackets, and we'd end up with G1 times G2 times G3 times Ni plus Ni1 plus G2 times G3 times Ni2 plus just G3 times Ni3. And that would be our total noise output power, NO. If I extract a factor of G1, G2, G3 from all of these terms, I end up with this. And if I write that like this, you might see that that has the same form as the expression that we used to separate out the noise contributions from a single stage amplifier. We have the gain of the amplifier here, the input noise, and then the equivalent input noise coming from the amplifier, Ne, where the gain is now the product of the gains of each of our stages, so it's the total gain of our amplifier chain, And our equivalent input noise for our whole chain of amplifiers here is given by this expression here. We can think about this in terms of moving the gain blocks around as well. If I'm trying to add in an amount of noise, NE2, at this point in the amplifier chain here, if I took that amount of noise, power, NE2, and divided it by the power gain G1, I could put an equivalent input noise here back at the input to my whole amplifier chain, give it the value NE2 over G1, and by the time this had got through the gain G1, it would be a noise power of NE2 again. Similarly, I can take this noise power NE3, move it back through the gains G2 and G1, replace it with an input noise NE3 over G1, G2 at the beginning of the amplifier chain. By the time this noise had got through the amplifiers G1 and G2, it would just be equal to NE3 again. So these two amplifier models give exactly the same output noise and output signal. Put that another way, this amplifier chain, this multi-stage amplifier, has an equivalent input noise given by the equivalent input noise of the first stage plus the equivalent input noise of the second stage divided by the gain of the first stage plus the equivalent input noise of the third stage divided by the product of the gains of the first two stages. And I could carry on like this. This is a well-known formula known as the Friis formula, and it tells you what the equivalent input noise of a multi-stage amplifier is going to be as a function of the equivalent input noises of each stage and the gains of each stage. Now, there's an important consequence of this formula, and that is this one. Provided G1 is large enough, the noise contribution from the second and all further stages of amplification are negligible. Means that almost all of the noise contributed by the multi-stage amplifier is going to be coming from the first stage, provided the first stage's gain is sufficient to reduce these second, third, and subsequent terms to negligible levels. This is why when you're designing amplifiers with multiple stages of gain, it's very important to pay attention to the noise performance of the very first stage, because that is likely to dominate the noise performance of your entire amplifier system. It's the reason why some very sensitive amplifiers, the kind of things they use in radio astronomy, have liquid nitrogen cooled first stage amplifiers in order to get their noise down to minimum possible levels. But subsequent stages of amplification, nobody cares very much. They don't have a big effect on the total noise in the system. We could perhaps see an example of this working. Supposing I had a three-stage amplifier. The first stage has a voltage gain of 30 and introduces an RMS equivalent noise of 10 millivolts. Stage 2 is exactly the same as stage 1. Stage 3 has a voltage gain of 1 but introduces 50 millivolts of noise. Which of these stages contributes the most to the total output noise of the system? Well, I can just substitute the numbers into the Friis formula, bearing in mind, of course, that all of these equivalent input noises are noise powers, so I need to take the square of the noise in volts, and these gains, G1, G2, are power gains, so I need to take the square of the voltage gain to calculate those. Substitute in all the values, and we can see the relative contributions of each of the stages. The first stage is introducing 100 microwatts of noise, which is 3 orders of magnitude more than the second stage introduces, and nearly 5 orders of magnitude more than the third stage introduces. In other words, almost all of the noise is being introduced by the first stage. The total equivalent noise of my entire system, in fact, 10.006 millivolts, whereas 10 millivolts of that is coming just from the first stage amplifier. The effect of the second and third stage amplifiers are to just introduce an additional 0.006 millivolts of noise. Negligible. That's all for this one. Next time I want to talk about noise temperature, which is another way of defining how much noise an amplifier stage introduces.